So here we have another polynomial function that we want to analyze. So we want to start off, before we even graph it or anything, to at least generate the expectations as to what, generally speaking, the graph will look like using the leading coefficient test. And so that's going to be done by using the highest exponent here, seeing that that's even, which means we're going to have a touchdown graph. And with a leading coefficient that's a positive 1, that means that we're going to be going up on both sides. So generally speaking, we're going to have a graph that looks something like this. Now, how high up or whether the dips are even with each other or what will be determined when we actually graph it. But we know for this one that we're going to have a touchdown graph where both sides are going to be going up. So that takes care of step 1 of our process. So for step 2 now, we actually want to go to Desmos or graphing calculator and plot the graph. So if we jump to the next screen here, we can see exactly that. So we enter our equation into Desmos, and then we can identify all of our key points here by just clicking on all these locations. And so indeed, we have a touchdown graph that matches up with what we were expecting based on the leading coefficient test. And then we can see that we've got a couple of zeros that are pretty user-friendly, -1, 0, and then 5, 0 right here. But then we have a couple others that are definitely some sort of square root value that we're going to have to solve for. So we're going to have to work on that. Then we also want to make sure that when we go to sketch our function that we're graphing it with a proper scale. So we can see on this one we have a pretty significant movement in the vertical direction. So down here we're at -60 up to +60. And then in the horizontal direction, though, we could still, on our original graph, count by 1s. And we should probably identify some key locations here. Again, we could just click on these locations if we're using Desmos to help us out. But this one here, we just want to get some ballpark estimates of these. So we're like -1.5-ish for the x coordinate, and then it looks like if we're counting by 5s for every single one of these tick marks, we're about -10. I just want to have this information so that I can sketch it on my other screen. I've got a y-intercept here of 25, and we can see that not just from the graph, but by just looking at the equation, whatever term does not have an x attached to it. This location here looks like it's maybe 0.75-ish, so let's say 1, comma, and then it looks like it's about 33. Again, if we clicked on that, we would get the exact value, but I'm just trying to get ballpark ideas so that I can get a rough sketch. And then down here at this location here, looks like we're right about at 4 as my x-coordinate and right about at -55 for my y-coordinate. And so I'm going to go back. I just want to be able to sketch that on my graph. Now, I could count by the same interval that we did before, but that'll be a little bit inconvenient since I have 10 units in each direction. So I'm actually going to count by 10s and go up to 100 and down to -100. I can't stop at 50 because I actually exceed that value on my graph. So I'm going to count by 10s. That'll make it easy. But then in the horizontal direction, I'm going to still count by 1s. I'm going to keep that consistent. And again, I'm just interpreting this from the graph that we generated on Desmos. So we had zeros at -2.36, so that's right about there. We had a 0 at -1. We had a 0 at +2.36-ish. And then we had a 0 at 5. So we've got our zeros marked out. And then I'm just going to mark out those local minimum and local maximum, those relative minimum, relative maximum points. So we're like -2, and we're counting by 10s, remember, in the vertical direction. So it's just going to be down 1 tick mark here. Over 1 up to 33, so that's going to be right about there. And then our last one was over 4 down 55. So if I count by 10s, 10, 20, 30, 40, 50, kind of halfway in between, puts me right about there. And so now that's enough for me to get a decent sketch of my graph. So now again, remember, we had those 2 zeros. There was one here that was at x equaled -1, and there was one right here at x equaled -5, or +5, sorry. So those are the 2 zeros that we're going to be able to use via synthetic division to get us from a polynomial that is a fourth degree, x to the fourth is the highest exponent, and knock it down to x squared so that we can then use some quadratic techniques, whether that's factoring or completing the square or square roots, as is most likely, to find what those two zeros are that were at the, whoops, let's try that again, at the negative 2.236 and positive 2.236. We want to know what that exact value is. So I'm going to set up my synthetic division. So I'm going to start off and I'm going to use this integer value here. So I'm going to have -1 as what I'm dividing by, and then let me just make sure indeed that's minus. So I need the coefficients: 1, -4, -10, 20, and 25. So now I'm going to roll through my synthetic division. I bring down the 1, multiply on the diagonals. -1 times 1 is -1. Add in the vertical direction. -4 plus -1, -5. Multiply. -1 times -5 is 5. Add. -10 plus 5 is -5. Multiply. -1 times -5 is 5. Add 20 plus 5 to make 25. One more multiplication. -1 times 25 is -25. One more addition. Indeed, we get 0. And we should always get 0 when we're testing these locations that we saw on the graph as integer values. Those will always work. So that takes care of one of them. But remember, this was the coefficient in front of x to the fourth. So this gets me down to x to the third, which is not low enough for me to use my quadratic techniques. So I need to also, in this case, divide by this other integer 0 that we observed from the graph, which is x equals 5. And so I'm going to go ahead and set up for that. So I've got the 5 here, and I roll through the exact same thing. I bring down the 1, and now I multiply 5 times 1 to get 5. Add -5 and 5 to get 0. 5 times 0 is 0. -5 plus 0 is -5. 5 times -5 is -25. Add one last time, and we again get 0, as we should, since we observed that 0 from our graph. And so now we've gone from x to the fourth to x to the third, and now this is the coefficient in front of x squared. So we can write this equation: x squared plus 0x, so there's no x there, and then -5 equals 0. And so now this is the equation we need to solve to find those remaining zeros, these zeros that had this decimal value. Now we're going to get that exact value. So I'm going to add 5 to both sides. I'm going to scroll down a little bit to give myself a little bit more room. So we get x squared equals 5. So now we can take the square root of both sides. And so we get x equals, and then I can't simplify that expression, but I need my plus or minus. So plus or minus the square root of 5. So altogether, all of my zeros on this problem, are x equals, I've got the two integer zeros that I observed from the graph, -1 and 5, and then we've got the plus or minus root 5 that we got after using synthetic division and our quadratic techniques over here. So we've got our 4 zeros for this polynomial function.